I from International University. Today I would like to talk about the both CFD model for the molten metal bubble column reactors. And my talk is divided by for part introduction. I talk about the molten metal bubble column reactors, the key process design of the MMBCR and the objective of this study. In the model description, I will describe the geometry and the governing equation of the model, geometry meshing, and especially the bubble detection algorithm that we introduce into the both CFD model. And next, we verify and validate our model. We analyze the hydrodynamics of this reactor, and we calculate the gas-liquid interfacial surface area, conclusion and future work. As we know that due to the environment warming nowadays, the mitigation of the greenhouse gas become more urgent, and also people are interested on the hydrogen or some net zero emission or some lower CO2 energy sources. And so that's why people are interested on the molten metal bubble column reactor. Actually, this process was developed for a long time ago, but at that time, because there are no catalyst, so it requires very high temperature. So this kind of process is have some disadvantage in the economical point of view. But nowadays, because of some development in the catalyst field, like we mix up some high activity metal into the low melting temperature metal. So that's why we can easily compose the methane into the hydrogen and the carbon. And also the similar study, the destruction of the F-gas also can be used by this way. So let me explain the key mechanisms in the bubble column reactor. That in the bubble column reactor, when we inject the gas at the bottom of the reactor, the gas will rise up, and because of the reaction appear here, the reaction in the bubble column reactor can be divided by three mechanisms. First one is the non-catalytic reaction, just like the thermal decomposition of the methane or some of the other gases, just in the volume of the gas with the velocity, the relative velocity almost zero. And the second mechanism is the catalytic reaction that takes place on the surface of the bubble. And the last mechanism is the mass transfer between the very thin layer near that surface. And in the bubble column reactor, because of the very complex mechanism between the liquid gas and the interface, so that's why we in order to design this reactor, we need to analyze the hydrodynamics problem, including the mixing, the reaction inside the volume and on surface, and also because usually for the bubble column reactor, the core annular flow, the behavior of fluid, so that's why we have the dispersion along the reactor height. And one more thing is that for this, the molten metal bubble column reactor, the carbon usually when we decompose some gas like methane or some like C3, it will produce a lot of carbon. So for most kind of the reactors, like a fixed bed reactor, because of that carbon, so the stagnant or some problem will appear. But for the molten metal bubble column reactor, the carbon will deposit on the surface of the bubble, and then it rise up, and then it float into the liquid level. So we easily can separate them. So the use of the molten metal bubble column reactor have another benefit on the separatable carbon particles. And so that's why they have some advantage in the economic point of view comparing with the others. However, the design of the reactor is very complex. It requires some key process design parameters such as the flow regime and the gas out. In the hydrodynamics, we need to know the flow characteristic and the dispersion coefficient. In the mass transfer, we need to know that the specific interfacial area, and we need to know the bubble size distribution. For the heat transfer, we also need to calculate the heat transfer because it depends on the velocity and also the bubble size. So most of the key design parameter of the bubble column reactors can be estimated or can be predicted by CFD simulation. So in this study, we want to, our objective are to develop the both CFD model for a molten metal bubble column reactors. And since most of the common CFD code have no algorithm to determine the bubble size distribution using the FOF, so that's why we need to add up to introduce the bubble detection algorithm into the commercial code. And using the both CFD model results and the bubble detection algorithm, we can calculate rigorously the process design parameter and to analyze the difference between the traditional and the new approach. The traditional approach can be like that. We can, through the experiment, we can measure the pressure drop, and then we can estimate the gas out based on that pressure drop and the density. From the experiment, we also can measure the bubble size, and the specific interfacial area can be calculated like indirectly using the gas up and the bubble size. But for this study, we want to apply the both CFD model. First of all, we validate the model, and then we directly calculate pressure drop, gas up, and we apply the bubble detection algorithm to directly calculate the bubble size distribution. And we directly calculate the specific interfacial area by this. Just sum up the interfacial area of each bubble and the volume of reactor. And this is the model description. We use this very small bubble column reactor with the gas was injected at the center of the reactor, and we have several assumptions like the model. We did not consider energy equation and not incompressible. We assume that the Newtonian fluid, so the viscosity is constant. There's no chemical reaction, and there's no solid carbon. There's no mass transfer between the gas and liquid. And the gas and liquid do not penetrate each other, and the size of the smallest bubble is greater than the computational cell size. And also that we did not count the solid carbon on the turbulent kinetics of the liquid phase. So this is a description of the both CFD model. We have two phases. The first is the gas phase, including the methane or the hydrogen, and the liquid phase is a molten tin. And we apply the LES fluid model with the subgrid scale model. It's WALE1, and also we apply the surface tension force and the wall adhesion force into the liquid phase. And the reason why we use VOF here that in the VOF with the sharpening velocity term in this equation, we can capture accurately the surface of the bubble comparing with the earlier or the other approach. So because our interest in the interface between the gas and liquid. So this is a mesh structure, and the number of cells is just more than 1 million cells, and we ensure that the cell size is just 0.7 millimeters. So that's why we can predict any bubble with the size higher than 0.7 millimeter. And in order to improve the accuracy of the both model on the interface, we apply modified RIC, the volume fraction displacement scheme, and we use the adaptive time step size to accelerate the computational time. And this is a bubble detection algorithm. This work was published in our papers recently, and also in the just accepted manuscript. Actually, the key idea of the bubble detection algorithm is like that. We assume that we define that the bubble is a closed volume with the gas volume fraction over 0.5. So means that we need to hold the CFD domain, and then we just mark up which cell will have the volume fraction over 0.5, and then we sum up that, and then we if two bubbles is close together, but their volume is do not attach together, so we decide it's just two bubbles. Yeah, so in order to remove the unreal bubble, we use the several filtering criteria, and then we test that the dependency between the filtering criteria on the performance of the reactor. And this is a model verification and validation. As we know that the LES is incomplete, so that's why the grid size should be determined by the CFD results, that we need to calculate the resolved turbulent kinetic energy to the sum up the resolved and the subgrid scale turbulent kinetic energy, and we need to ensure that most of the cell within the volume must be higher than 80%, and then you can see that most of the cell is higher than 80%, so the current cell size is enough for the LES. And also we also validated our model against the experimental data in the literature using a different geometry. And let's move into the hydrodynamics of the reactor. We can see that the pressure drop of this reactor is around 22.4 kPa, and most of the bubble is concentrated near the injection tube. And if we see that there are two contours, one left-hand side is just the axial velocity, and right-hand side is the time average of the axial velocity. We can see that in the time average axial velocity, we see that most of the gas is rise up at the center and fall down near the wall. So the core annular flow and very high axial dispersion coefficient is expected in this reactor. And also by applying the bubble detection algorithm, we can calculate directly the bubble position and along the reactor height. We see that we can see some mechanism, some bubble breakup and the bubble coalescence mechanism appear in the bubble current reactor. And we also tested the influence of the filter size on the bubble density, bubble beam size, the gas liquid interfacial area. Even though the bubble density change much with the different filter size, but the southern mean diameter and the gas liquid interfacial area almost is effect not so much, just around less than 10%. The next is we calculate gas liquid interfacial area. We compare with the traditional method and the new method. In the traditional method, we calculate the volume fraction of the gas, like a gas go up. We calculate the means, the outer mean diameter, and then we can calculate the gas liquid interfacial area of this reactor, just 0.3. But when we apply the both CFD model with the bubble detection algorithm, and then we calculate directly based on the surface area of the all bubbles and divide to the bubble to the reactor volume, we obtain that around 25 times higher the interfacial surface area. And also we compare our CFD model with the common bubble specific surface area in the literature. It's slightly different with the bubble interfacial area. It's this surface of the bubble per reactor volume, but this one is the surface of bubble per bubble, all bubble volume inside the reactor. So we see that our CFD result is between the common value from the literature. And I would like to conclude our work on the both CFD model, and we developed the both CFD model for the molten metal bubble column reactor. We applied the bubble detection algorithm, and we found that this reactor have a high axial dispersion and the core annular flow. We also see that both breakup and collection appear. By applying the rigorous gas liquid interfacial area calculation method, we found that around 25 times higher value of the interfacial area than the common calculation method, and the specific surface area prediction agree well with the literature experimental data. By using the both CFD model and the bubble detection algorithm, we can predict almost the key process design or the reactor design, such as the gas collapse, outer mean diameter, bubble rising velocity, gas liquid interfacial area, and so on. Yeah. And this work was supported by NIF. Thank you for your attention. Any questions?
질문이나 코멘트 있으시면.
Thank you for your nice presentation. I'm sorry I came in the middle of your presentation. So how did you validate your model with experimental data? Did you get experimental data from your own, or you get?
Yeah. Actually, not yet. We do not have any experimental data for but we already validated our model with the literature data for different molten metal, not for the tin. Actually in this study we validated. In this study we validated with our own experimental data in the pressure drop. Without any reaction.
Without any reaction.
Yeah.
So I have one question. So you wanted to use this reactor for 3 reactions producing solid particles. But you neglected the effects of the solids.
Actually,
so can you comment on the effect of those particles?
Thank you for your question. That this process, this type of reactor can be applied for 3 kind of processes. But in this study, I just example, the first is the methane decomposition, and the plastic waste and the F-gas decomposition. It will be another study, but using the similar the molten metal bubble column reactor like in this study. So actually in the future, if we apply the reaction, just only one of them, like in this study, if we apply the reaction, just the first one, and the others study is the plastic waste or the F-gas. Yeah, actually, the cell size. First of all, the cell size should small enough to capture the 80% of the turbulent kinetic energy of the LES. This is just the first requirement. The second requirement is that we need to test the cell size to ensure that most of the bubble is captured by the different. Even here, I apply the different filters. Filter size means that different cell size. With the filtering criteria is 4. It means that the bubble size should compose by at least 4 cells. So that's why we see that it have a little bit dependence on the cell size. But if the other case, if we have the other bubble column reactor, maybe in higher velocity, it belongs to jetting regime. Maybe the cell size will be different. But for this kind of bubbling, the bubbling regime is enough. Is already enough for the cell size.
네.